Okay, here's problem 3.8 in the problem solving videos. We're going to be finding V0 using nodal analysis, and we're going to be following the problem solving strategy on page 102. So let's start off first by identifying the nodes in the circuit. So we have a node at that point, this point, this point. We have a node here, and then one on the bottom. So now we have 5 nodes. Okay, and then we're going to select one as a reference node, and since we're going to solve for V0, let's pick the bottom node as a reference, and that will allow us to solve for V0 directly. So now we have 4 node voltages. Okay, one of them is V0. Let's label the other ones. Let's label this one V1, V2, this one V3. Okay, so our node voltages then are V1, V2, V3, and V0. Now, we know one of our node voltages because in this circuit we have a voltage source connected between a node and the reference node. So then we know that node voltage V3 is 12 volts. Okay, so that leaves us with 3 unknowns, V1, V2, V0. So we're going to need 3 equations, okay, to solve for V1, V2, and V0. So now our plan is to apply KCL at these 3 nodes to come up with our 3 equations. So let's start with the node corresponding to V1. And again, we'll sum currents leaving through resistances and set it equal to the sum of currents entering from sources. So if we start, we'll have V1 over 3K. Okay, there's a current leaving down through that resistance. This current, we have V1 minus V2 over 6K. And then we have 8 milliamps entering, 2 milliamps leaving. Okay, and then we can take our equation in and just collect up some terms, and we'll have 1 over 3K plus 1 over 6K times V1 minus 1 over 6K times V2 is equal to 0.006. So there's one of our equations. Now we need 2 more, and we're going to get those by applying KCL at those other 2 nodes. So now we're going to apply KCL at this node and this node. Okay, at the center node, we're going to have a current leaving that's V2 minus V1 over 6K. A current leaving through here that's V2 minus V3 over 6K. And then a current leaving through here is V2 minus V0 over 2K equal to 0. And let's collect terms. We have minus 1 over 6K V1. Then we have 1 over 6K plus 1 over 6K plus 1 over 2K times V2 minus 1 over 6K times V3 minus 1 over 2K times V0. So there's our second equation. Now let's go ahead and substitute in that V3 is 12 volts. Okay. And if we do that and rearrange this equation, we'll have minus 1 over 6K times V1 plus 1 over 6K plus 1 over 6K plus 1 over 2K V2 minus 1 over 2K times V0 is equal to 0.002. Okay, so here is our second equation. Now, let's apply KCL over at the node on the right. And if we do that, we'll have V0 minus V2 over 2K. That's the current leaving that direction. Here we have V0 over 1K. That's the current leaving down. And then we have a current entering that's 2 milliamps. And then we can rearrange this equation to give us minus 1 over 2K times V2 plus 1 over 2K plus 1 over 1K times V0 equal to 0.002. There's our third equation. So now we're ready to solve the equations, and if we write them in matrix form, then our equations become the following. So now we're just copying the equations down into matrix form. And we have V1, V2, V0. And now our current vector becomes the following. Now, using MATLAB to solve, we get the following voltages. And here's our answer, V0, as shown.